This is video 4.14, which is a continuation of video 4.13 on principal component analysis. In this video, I will talk about figures 4.4, 4.5, and 4.6 in your text on pages 180 and 181. Now, if we go back to the Excel spreadsheet that we had in video 4.13, you can see here that I've highlighted a matrix here. These are the scores of each of the 6 persons on the 2 principal components that were extracted from the covariance matrix. And we will use that here in a little bit within the next 2 videos, actually. Now, in your text, figure 4.4 shows the input matrix of data on the 6 male subjects and their scores on each of the tests. We have the verbal test, the math test, and the logic test. And here's Al, Bill, Charlie, Dan, Ed, and Frank, and their scores on those tests. To the right of the matrix, we have plotted the point for each subject in the 2-dimensional space with math test score on the horizontal axis and verbal test score on the vertical axis. Now, the convention is having the first variable on the horizontal and the second on the vertical, but for aesthetic reasons, we have violated that usual convention. And just to show you it better here, so we get A for Al. He scores 8 on verbal test and 12 on math test. So we'll go 8 up and to 12 over here, and so on. Since these demonstration data were created to have linear dependency, that is, created to have a rank of 2, the third variable, the logic test, is located within the same two-dimensional space as we see here in figure 4.5. And this actually should be math, and this is verbal. I apologize for that. Now, had this matrix not been a rank of 2, reasoning would come out of the page and it would kind of create an ellipsoid. So this 2-dimensional space is easy to comprehend, but the same principle is demonstrated here, generalized to larger data sets of actual practice. When you have, you don't have a rank of 2 matrix, maybe more variables. Now, the 2 advantages of principal components are that these are orthogonal to one another, as we see here, and they account for largest amount of variance possible in descending order from the first factor to the second to the third, and so on. The maximization of variance by PCA can be shown with this simple demonstration data. Now, looking at figure 4.6, the first principal component is in fact the major axis of the ellipse enclosing the scatter plot of the data. It is the longest possible line passing through the ellipse in its center. So that is component 1. This is another way of seeing that it maximizes the variance because it is the largest possible line passing through the center. Successive principal components are minor axes of an ellipsoid within many-dimensional space, with each accounting for maximum amount of variance orthogonal to all previous components, as discussed in your text down here. Now, what's that saying is, well, since we have a matrix of rank of 2 or data with rank of 2, we only have 2 components. So the second component, component 2, which we labeled as verbal, is going to be the minor axis, which of an ellipsoid is the longest possible line being orthogonal to the major axis. Now, had logic this not been rank of 2 and logic would play a factor here, like I said before, it would stick out of the page and we'd have a 3D ellipsoid. And that component, component 3, would be the longest possible line going through the center, also orthogonal to these. So it's kind of hard to draw. but as you see in figure 4.5, it would kind of go like this, up out of the page. So that's it for this video. It was just to get an idea of how what we did in video 4.13, the one previous to this, how that looks geometrically and everything. So I hope that makes sense for you. Take care. I'll see you in the next video.